Welcome! In this session, we'll explore problem number 285, Inorder Successor in BST. This problem focuses on traversing binary search trees and identifying the next node in in-order traversal. It's a foundational concept in tree algorithms and a great addition to your problem-solving toolkit. Let's dive in. The problem asks us to find the in-order successor of a given node in a binary search tree, or BST. The in-order successor of a node is the node with the smallest value that is strictly greater than the given node's value. If no such node exists, we return null. The function takes two inputs. The first is the root of the BST, which represents the entire tree, and the second is the node p, whose in-order successor we need to find. The output is either the in-order successor node or null if there is no successor. This problem is fundamental in understanding tree traversal and utilizes the properties of a BST to efficiently find the solution. Let's consider the first example. The input is a binary search tree with the structure shown, where the root is 2, it has a left child of 1 and a right child of 3. The node p is given as 1. Our task is to find the in-order successor of the node with value 1. The output of this example is 2, which is the next node in the in-order traversal of the tree. This behavior aligns with the problem description because 2 is the smallest value greater than 1 in the BST. To explain the output further, we perform an in-order traversal of the BST. The traversal visits the nodes in the following order: 1, 2, and then 3. For the node p with value 1, the next value in this sequence is 2, so 2 is its in-order successor. Now, let's look at another example where the tree is more complex. The input tree has the root value 5, with children 3 and 6. Then, 3 has its own children, 2 and 4, and 2 has a left child of 1. The node p in this case is 6. The output for this example is null. After performing an in-order traversal of the tree, we get the sequence 1, 2, 3, 4, 5, 6. The node p has the value 6, which is the largest value in the tree. Since there are no nodes with values greater than 6, it does not have an in-order successor, so the function returns null. This demonstrates one of the important edge cases where the given node is the largest in the BST. Now, consider a third example. In this example, the tree has a root value of 15, with children 10 and 20. The left subtree of 10 contains 8 and 12, while the right subtree of 20 has 16 and 25. The node p is 10. After performing an in-order traversal, the sequence is 8, 10, 12, 15, 16, 20, 25. For the node p with value 10, the next value in the sequence is 12, so its in-order successor is 12. This highlights the scenario where the in-order successor is found within the left subtree of the right child. There are a few additional points to consider in this problem. If the given node p is the largest node in the tree, the function should return null, as there is no successor. If the tree has only one node, the in-order successor is also null. Another key observation is that if p has a right subtree, the in-order successor is the leftmost node in that right subtree. However, if p does not have a right subtree, the successor will be one of its ancestors, specifically the lowest ancestor for which p is in the left subtree. These constraints and edge cases are crucial for implementing a robust solution. To solve the problem of finding the in-order successor in a BST, one straightforward approach is the brute force method. The idea here is simple: perform an in-order traversal of the BST, which naturally visits the nodes in sorted order. During the traversal, we store all the nodes in a list. Once we have the list, we locate the node p in the sequence and return the next node, which would be the in-order successor. The steps are clear. First, traverse the entire tree and collect all nodes. Then, find the index of p in the list and return the node at the next index. If there's no such index, we return null. While this approach is easy to understand and implement, it comes with some trade-offs. The time complexity is O(n), as we traverse the entire tree and also search for p in the list. The space complexity is also O(n), because of the extra list we use. The main drawback is that this method doesn't utilize the properties of a BST, making it less efficient than other potential strategies, especially for large trees. By leveraging the properties of a BST, we can develop a more efficient and optimized approach. Recall that in a BST, values in the left subtree are smaller than the root, and values in the right subtree are greater. This structure allows us to navigate the tree more intelligently. The key insight here is that the in-order successor of a node P is the smallest node in the tree that's larger than P.val. If P has a right subtree, the successor is simply the leftmost node in that subtree. However, if P does not have a right subtree, the successor must be one of its ancestors, specifically the lowest ancestor whose value is greater than P.val. Using this insight, we can traverse the tree iteratively. As we move through the tree, we maintain a variable successor to store the current best candidate. If the root's value is greater than P.val, we update the successor and move left. Otherwise, we move right. This approach efficiently narrows down the search space, and the time complexity is O(h), where h is the height of the tree. For balanced trees, this is O log n, and even in the worst case, it's O(n). Importantly, the space complexity is O(1), as no extra data structures are used. This optimized iterative approach significantly improves efficiency, but it's worth noting the trade-offs as we compare alternative methods. One such alternative is the recursive implementation of the same logic. Here, instead of maintaining the successor variable explicitly, we use the function call stack to keep track of potential successors. The recursive algorithm works by checking the root's value and making recursive calls to either the left or right subtree, passing the current root as a potential successor if its value is greater than P.val. While this recursive approach is elegant and concise, it introduces additional space complexity due to the recursion stack, which can go up to O(h). This could become problematic in deeply skewed trees, where the recursion depth may lead to stack overflow. Thus, while both the iterative and recursive approaches share the same time complexity of O(h), the iterative version avoids the risk of stack-related issues, making it more robust for large or unbalanced trees. Considering the various approaches, the optimized iterative strategy stands out as the best choice. It strikes the right balance between simplicity, efficiency, and reliability. By taking advantage of the BST's properties, this method avoids unnecessary traversal and doesn't require extra storage, making it far more scalable than the brute force method. Compared to the recursive alternative, it eliminates the risk of stack overflow, which is especially important when working with deeply skewed trees. These qualities make it the most practical and robust solution for finding the in-order successor in a BST, ensuring it performs well across a variety of tree structures and sizes. In this problem, we are tasked with finding the in-order successor of a given node in a binary search tree, or BST. The in-order successor of a node is the next node that would appear in an in-order traversal of the tree. If there is no such node, we return null. To start, let's examine a brute force approach to solve this. The intuition here is to take advantage of the properties of in-order traversal, which visits nodes in sorted order for a BST. First, we perform an in-order traversal using recursion. This involves visiting the left subtree, then the root, and finally the right subtree, while storing each visited node in a list. Given that the nodes are stored in sorted order, the next step is to locate the given node P by iterating through the list and comparing values to find a match. Once P is found, we simply return the next node in the list if it exists. If P is the last node in the list, we return null since there is no successor. If the node P happens to be the last node in the list, our algorithm will return null, as no successor exists in this case. Now, let's account for edge cases. If the tree is empty, we immediately return null since there are no nodes to process. Similarly, if the node P does not exist in the BST, we return null as well. To implement this brute force approach in code, we start with a helper function for in-order traversal. This recursive function takes the root of the BST and a list to store the nodes. It traverses the left subtree, appends the current node to the list, and then continues with the right subtree. Using this helper function, we can create the main function to find the in-order successor. First, we perform the in-order traversal to populate the list of nodes. Then, we iterate through the list to locate node P. If we find P and it's not the last node, we return the next node in the list. Otherwise, we return null. This approach is simple and guarantees correctness but has some limitations, which we will explore next. The brute force approach provides a clear and straightforward way to find the in-order successor, but it comes with certain trade-offs. By performing an in-order traversal, we ensure the nodes are visited in ascending order, making it easy to locate the successor. The linear search through the resultant list is direct and ensures accuracy. However, this approach requires storing all the nodes in a list, leading to an O(n) space complexity, where n is the total number of nodes in the tree. When analyzing the time complexity, the in-order traversal itself takes O(n), and searching for p in the list also takes O(n). Therefore, the overall time complexity is O(n). While this solution is effective in smaller or medium-sized trees, the extra space required for the list can become a limitation for very large trees. This approach is not the most space-efficient, as the list doubles the memory usage, which can be problematic if the tree contains a significant number of nodes. Considering these limitations, we can explore optimizations to improve the efficiency of this algorithm. One key observation is that traversing the entire tree and storing all nodes in a list may be unnecessary. If the node P is located early in the traversal, we don't actually need to process the rest of the tree. This insight leads us to consider optimization possibilities. Instead of using an additional data structure like a list, we can leverage a pointer-based approach to find the successor more efficiently. By directly traversing the BST, we can identify the in-order successor without storing all the nodes. This method not only reduces the space complexity but can also minimize the time spent traversing the tree. Such an optimized approach takes advantage of the BST structure, allowing us to make comparisons and selectively traverse only the relevant parts of the tree. This way, we can avoid unnecessary computation and achieve better performance for both time and space. This solution efficiently finds the in-order successor of a node in a binary search tree, BST. The in-order successor of a node is the next node in the in-order traversal of the BST, which is the smallest node larger than the given node. Let's go through the code step by step. 1. TreeNode class. The TreeNode class represents a node in the BST. Each node has a value, val, a left child, left, and a right child, right. 2. Solution class. The solution class contains the Inorder Successor method, which implements the algorithm to find the in-order successor. 3. Initialize successor. The successor variable is initialized to none. This variable will hold the potential in-order successor as we traverse the BST. For traversal logic, the algorithm uses a while loop to traverse the BST. If the value of the target node P is less than the current node, root.val, the current node is a potential successor because it is larger than P. We store this node in successor and move to the left subtree to check for smaller potential successors. If P.val is greater than or equal to root.val, we move to the right subtree because the in-order successor must be larger than P. 5. Return result. Once the traversal is complete, the successor variable contains the in-order successor of P if it exists. If there is no successor, the method returns none. #efficiency. The algorithm relies on the properties of the BST and avoids the need for an explicit in-order traversal, making it efficient with a time complexity of O(h), where h is the height of the tree. In a balanced BST, this is approximately O log n. The space complexity is O(1), because no extra space is used beyond the variables. ### edge cases. If the input node P has no in-order successor, e.g., P is the largest node in the tree, the algorithm correctly returns none. If the BST is empty, root is none, the method handles this gracefully and returns none. This solution is concise, efficient, and leverages the BST properties effectively to find the in-order successor without unnecessary computations. Here, we start by defining the TreeNode class, which represents a single node in our binary search tree. Each node has a value, along with references to its left and right child nodes. The constructor initializes these values, with the left and right pointers set to null by default. Next, we define the solution class and its method Inorder Successor. This method takes the root of the binary search tree and the target node P as input, and it returns the Inorder Successor of P. The Inorder Successor is the smallest node in the tree that is larger than P. Within the method, we declare a variable successor and initially set it to null. This variable will hold the potential successor as we traverse the tree. The traversal begins with a while loop that continues as long as the root is not null. Inside the loop, we compare the value of the target node P with the current root node. If the value of P is smaller than the root's value, it means the current root could be a potential successor, so we store it in the successor variable and move to the left subtree to explore smaller values. On the other hand, if the value of P is greater than or equal to the current root's value, it means we need to look for the successor in the right subtree, so we update the root to point to its right child. This process continues until we either find the successor or reach the end of the tree. Finally, once the loop exits, we return the successor variable. If no successor is found, the method will return null, indicating that the target node does not have an inorder successor within the tree. This approach ensures that we efficiently traverse the tree while maintaining the constraints of a binary search tree, checking only the relevant nodes to identify the inorder successor. To find the inorder successor of a node in a binary search tree, we start by comparing the value of the target node, P, with the value of the root node. In this example, the target node is 3. First, we begin at the root, which is node 5. Since 3 is less than 5, node 5 becomes a potential successor. We then update our successor variable to 5 and move to the left subtree because the inorder successor, if it exists, must be smaller than the current successor but larger than 3. Now, we're at node 3. Here, 3 is equal to the value of the target node, so we dismiss this node as a potential successor and move to the right subtree to continue the search. The right child of node 3 is node 4. At node 4, we compare the values again. Since 3 is less than 4, node 4 becomes a new potential successor. We update the successor variable to 4 and proceed to the left subtree to ensure there's no smaller value that still satisfies the conditions. However, the left child of node 4 is none, so we terminate this part of the search. At this point, the root pointer has reached none, which means we've traversed the necessary path in the tree. The final value of the successor variable is node 4, making it the inorder successor of node 3. Now let's consider a second example where the target node, P, is node 4. We begin again at the root, node 5. Since 4 is less than 5, node 5 becomes a potential successor. We update the successor to 5 and move to the left subtree, which brings us to node 3. At node 3, we compare values again. This time, 4 is greater than or equal to 3, so we move to the right subtree to explore whether a closer successor exists. The right child of node 3 is node 4. At node 4, we find that 4 is equal to the target node's value. According to the conditions of our algorithm, we move to the right subtree of node 4 to continue the search. However, the right child of node 4 is none, so we terminate the loop here. Since the traversal ends with no further nodes to consider, the value of the successor remains node 5, which was the last valid potential successor updated during our traversal. Thus, for the target node 4, the inorder successor is node 5. Now let's explore what happens when the target node is the largest node in the tree. In this third example, the target node is 6. Starting at the root, node 5, we compare 6 with 5. Since 6 is greater than or equal to 5, we move to the right subtree to search for a successor. The right child of node 5 is node 6. At node 6, the target node's value matches the current node's value. Following the logic of our algorithm, we move to the right subtree of node 6 to continue the search for a successor. However, node 6 has no right child, so the pointer moves to none, and the search terminates. At the end of the traversal, no potential successor was found because there were no nodes greater than 6 in the tree. As a result, the successor variable remains none. This means node 6 has no inorder successor. From these examples, we can summarize a few key observations about the algorithm. First, if the target node's value is less than the current node's value, the current node is a potential successor, and we move to the left subtree. Second, if the target node's value is greater than or equal to the current node's value, we move to the right subtree. Finally, the loop terminates when the traversal reaches a none pointer, and at that point, the successor variable will hold the result. This algorithm is highly efficient, with a time complexity of O(h), where h is the height of the binary search tree, because it only traverses a single path from the root to a leaf. The time complexity of the provided solution is O(h), where h represents the height of the binary search tree. This is because the algorithm performs a single traversal down the tree, starting at the root and then moving either to the left or the right subtree depending on the relationship between the target node, P, and the current node. In the worst case, the algorithm may need to visit every level of the tree exactly once. For a balanced binary search tree, the height, h, is approximately log n, where n is the total number of nodes, resulting in a time complexity of O log n. However, for a skewed tree, where each node only has a single child, the height h becomes equal to n, leading to a worst-case time complexity of O n. In the best case, if the tree is empty or the target node P is located right at the root, the algorithm terminates immediately, giving us a time complexity of O1. On average, for a balanced binary search tree, the time complexity remains O log n, but again, for an unbalanced or skewed tree, the time complexity stretches to O n. The space complexity of this solution is O1, because it uses a constant amount of extra space. Specifically, it relies on a single variable, successor, to store the potential inorder successor during traversal. Since the algorithm is iterative, it avoids additional memory overhead such as recursive stack space. This ensures that no matter how large the input tree is, the memory usage remains constant. Now, if we compare this optimized solution to a brute force approach, the difference becomes clear. A naive solution would involve performing an inorder traversal of the entire tree, storing all nodes in an array or list, and then finding the successor of the target node, P, within that array. This would lead to a time complexity of O(n) for the traversal and a space complexity of O(n) for storing the nodes. In contrast, the optimized solution avoids unnecessary traversal and storage. By leveraging the properties of the BST, it directly identifies the successor during the traversal, achieving a time complexity of O(h) and a space complexity of O(1). To further confirm the time complexity, let's look at the mathematical reasoning. In a balanced binary search tree, the height h is approximately log n. Since the algorithm traverses at most h levels, this results in a time complexity of O log n. On the other hand, in a skewed binary search tree, where all nodes have only one child, the height h equals the total number of nodes, n. In such cases, the algorithm traverses all n levels, giving us a time complexity of O(n). Overall, the complexity is directly proportional to the height of the tree, which is why the time complexity is expressed as O(h). In summary, the optimized approach achieves a time complexity of O(h), where h is the height of the tree, and a space complexity of O(1). This makes it significantly more efficient compared to the brute force solution, especially for larger trees. By minimizing both time and space usage, the optimized approach offers a clear advantage for solving the problem of finding the inorder successor in a binary search tree. Common mistakes in solving the inorder successor in BST problem often stem from overlooking key edge cases or misapplying the problem's concepts. For example, if the node P is the rightmost node in the BST, it has no inorder successor, and the function must return null. Failing to account for this can lead to runtime errors or incorrect results. Another frequent error is confusing the inorder successor with the inorder predecessor. Remember, the successor is the next node in the inorder traversal, while the predecessor is the previous node. Mixing these up results in the wrong output. Additionally, some solutions attempt a brute force approach by traversing the entire tree and storing nodes in a list. While this may work, it uses unnecessary O(n) space and ignores the efficiency offered by BST properties. Lastly, don't forget the case where P has a right subtree. In such cases, the inorder successor is the leftmost node in the right subtree. Missing this important property will lead to incorrect results. Another critical edge case to consider is when the node P does not exist in the BST. Before attempting to find the successor, ensure the node is present in the tree, otherwise, your solution may encounter runtime errors. Now, when it comes to interview scenarios, there are key patterns to recognize. The inorder successor depends on whether the node has a right child. If it does, the successor lies in the right subtree. If it doesn't, the successor is the first ancestor where the node is in the left subtree. Recognizing this distinction is fundamental to solving the problem efficiently, as it leverages the sorted nature of inorder traversal in a BST. Interviewers may also ask follow-up questions such as how to find the inorder predecessor instead of the successor, or how to solve this problem iteratively without recursion. They might also challenge you to adapt the solution for a binary tree that is not a BST, which would require a different approach. Understanding related problems can deepen your grasp of the concepts involved. For instance, LeetCode 94, which focuses on binary tree in-order traversal, is foundational knowledge for this problem. LeetCode 285 is essentially a variation of this same problem but with slightly different constraints, making it an excellent practice opportunity. Another related problem is LeetCode 173, where you implement an iterator for in-order traversal of a BST. This problem shares similar principles, particularly around navigating the tree efficiently. Lastly, LeetCode 230 asks you to find the kth smallest element in a BST, which also relies on in-order traversal and understanding BST properties. These problems collectively reinforce the importance of leveraging sorted order and traversal techniques in BSTs. There are multiple approaches to solving this problem, each with its own trade-offs. The brute force method involves performing an in-order traversal, storing the nodes in a list, and then searching the list to find the successor of P. While this is straightforward to implement, it requires O(n) time for traversal and an additional O(n) space for the list, making it inefficient. A more optimized solution uses recursive BST traversal. By leveraging BST properties, you can identify the successor during the traversal without storing all the nodes. This approach has a time complexity of O(h), where h is the height of the tree, and a space complexity of O(h) due to the recursion stack. Alternatively, an iterative traversal eliminates the recursion overhead. Using a while loop, you maintain a pointer to the potential successor as you traverse the tree. This approach is also O(h) in time but reduces space complexity to O(1). Both optimized methods require careful handling of edge cases, but they are significantly more efficient than brute force. Thanks for joining me on this walkthrough of Inorder Successor in BST. We reviewed the problem, discussed a brute force approach, and highlighted the importance of tree traversal techniques. Don't forget to practice similar problems to strengthen your skills. See you in the next session, and happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!